Thank you. So the cars that drive in the opposite direction do not disturb each other. More, if we have 4 cars, each of them is turning right, do they need any synchronization between them? Not at all. They can drive freely. So what do you think? How the resources in such a crossroads should be organized? What is the resource for which the cars compete? Having in mind that 4 cars turning right do not disturb each other. Well, what is the resource here? It's obvious. A quarter is a resource. Here, every car takes separate resource. But if we have one car entering the crossroad and one continuing its trip, they can fall into a conflict. We assume in such a situation that in Poland, according to the driving rules, the car on the right has privilege. But recall what we discussed about cooperation in this slide set. I will recall synchronization. Okay. Okay. Oh, here. Just recall the rules. If the resource is free, of course, all processes that want to take this resource do not occur exactly at the same time. One of them is first, and it takes the resource. So if the resource is free, a car just takes this quarter, regardless of the direction from which it comes. It's first rule, where if the resource is free, take it. During occupation of this resource, other cars can occur and compete. For this resource. in that moment, we realize the privilege. If we release the resource, and many processes wait for this resource, we choose one that has highest priority. So I will repeat what I said before. Blocking operation, like peon semaphore, wait on condition, is for safe allocation of resources. Resuming operation, like V-on semaphore, signal on condition, is scheduling operation, mutual scheduling. It has nothing to do with the operating system scheduling. It's mutual scheduling. A process tells which process is the next. It's mutual scheduling. So blocking is for safety, resuming is for scheduling. So when a process occupies resource and releases it, it can just release, not appointing another process, but it can appoint another process that will continue on this resource. However, to do that, we must have some distinction between them. Our priority semaphore that we programmed last time is just an example of the synchronization mechanism in which we can choose. We can divide waiting processes into two classes. And choose first from the class of higher priority. If it's empty, lower priority. Let's try to program such a cooperation rules. Okay. So a road cross is a class. We will use, the font is too small. Okay, it's better. We will use 4 priority semaphores. Each of them controls a single quarter of the crossroad. So it's priority semaphore, quarter, 4 elements. Drive. The parameter of drive will be the direction from which the car occurs. And source. And the second parameter, the destination. And we will number the quarters counterclockwise, because this is in the right hand movement. It is the order in which a car takes the quarters, for example, turning left. Okay. So first, the car takes the quarter of source P with privilege. With privilege, because the car entering the crossroad is on the right to the other cars driving from south or driving from west. It is on the right. So it is a privilege. So just remind me, the highest priority was 0 or the highest number in the implementation of. You can check. Let's look in history. Oh, it's not this solution. Oh, primary priority semaphore. It first checks priority. It's Boolean. Okay, because it's Boolean, the privilege is true. Okay. And if destination is source +1, of course, modulo 4, we simply leave the crossing. Okay. But if destination is source +2 modulo 4, we need release our first quarter and take the next one. Modulo 4 P. When I am on the crossroad, I am without privilege, because the privilege is for the right hand. So false here. And finally, V. Else, let us assume that the car can drive to the right, straight, and to the left. No turning around on the crossroad. Just right, left, and straight. So the third possibility is turn left, Q. Then I take the next one, next quarter. Okay. And V. And the third one. +2, +2. That's all. Look that we do not want any synchronization on the crossroad level. We need only synchronize the cars on the quarters. No new synchronization on the crossroad level. Now, of course, we need to initialize for int every semaphore is initially 0. Okay, but let's look. Assume that this car has dematched. It failed and stays in this quarter, occupies. Of course, it occupies. We should call some road service, but until they come, it occupies this quarter. So look what happens. Maybe there are two other quarters here and here, and cars take this quarter, release this quarter, and a car stays virtually between those quarters. And next one, next one, next one. And we have infinite queue of cars standing between the quarters. It's not possible physically. How to solve it? the solution is easy. We must take the next quarter before we release the previous one. That's all. So we just swap those two operations. And those two operations. Okay. Now this solution is free from this disadvantage. Okay. Let's analyze another problem. It can happen that 4 cars drive straight. What will happen? What could happen? It could happen that this car waits for this one, this for this one, this for this one. Okay? How to secure the solution? It is just a deadlock. What the driving rules say about such a situation? They say nothing. When we follow exactly the law, we should die by starvation because no one can leave the crossroad in such a situation, and we will wait forever. But if we take automatic control over the traffic, we can add additional rules not existing in traffic law. Please think, what solution from our previous analysis can fit to this problem? Do you recall butlers? Dijkstra butlers? Of course, we can use the butler that allows how many cars to enter the road cross? 3. If we allow only 3 cars, a deadlock will not occur. Okay? So let us add a general semaphore let it be butler and here we butler execute butler P and here butler V. and the initial value is 3. Okay. But please think. A deadlock occurs when a process has a resource and applies for a next resource, okay? Does it apply to all situations? What process never falls in such situation that it occupies a part of the crossroad and applies for another part? It is a process that turns right. It takes the resource and releases, and it does not take any other resource. So they do not fall into a deadlock. More, we can have 4 cars that turn right. And it is free from deadlock. So it is better to protect only the cars that go straight or left. So I will move this instruction only if we go straight or turn left. Okay. Let us complicate this exercise. We allow ambulances to enter the crossroad. What is the rule for ambulances? They have privilege over all cars. Okay. But between them, between ambulances, the rules are ordinary. So we must have a primary semaphore with 4 levels of priority, not 2. I think that you can program the semaphore with more than 2 levels of privilege yourself, because it's easy to enhance the previous solution. I would only add a parameter to the semaphore number of levels. 4. So this parameter, number of priorities. Okay, and it is additional parameter is the ambulance. Okay. Okay. Here, always if we, okay, if we are ambulance P with priority, let us assume that the greater the number, the higher priority. So it takes with priority 3, else Q source P of priority 1. Okay. Q okay. And here, if it's ambulance, we have the priority 2. Else priority 0. And the same here. Here, ambulance priority 2. Here, else. Okay. Okay. Of course, such a exercise can be complicated in many ways. We can give privilege one of the roads. We can program roundabout in which we have different rules. We can add trams that have middle priority between ambulances and cars, and so on and so on. We can complicate it, but you see that every complication just needs small intervention into the code. Why? Because it is programmed structurally. Okay, I will copy this solution to your chat. Chat, okay. And please be ready for a synchronization problem in midterm test. Okay. Do you have any questions? I have a book in Polish for a PT with exercises on synchronization. I will send this book to you. You can use some automated translator, I think. Oh, but the exercises themselves are just a code that is independent on the language. Where do I have this book? Rating system. I will upload this to synchronization. And I wrote a letter to the students last year about typical errors the students make in synchronization solutions, where I have this, maybe here. Oh, yes. I upload this to your channel. Huh? Okay. Synchronization is not easy, but it requires in equal proportions skills and thinking about given problem, because there are no general rules of solving synchronization problems. Okay. So if there are no questions, maybe now we will start the next topic, that is memory organization. Okay. Here is what the programmers expect from memory management. They expect that they will get large amount of memory that is extremely fast, because the speed of programs depends directly on the access time to memory cells, and to be non-volatile. However, static memory is so expensive that it is used only in very expensive computers. Ordinary computers have dynamic memory that uses it, that loses its content after turning the computer off. Typically, we have some hierarchy of memories. The fastest memory is registers inside a processor. The access time is nanoseconds for registers, so this is extremely fast. However, modern processors have quite large set of registers. RISC architectures can have more than 100 registers. And of course, the greater is the set of registers, the longer is the access time. Also, we have primary memory of a computer with access times about 100 times slower than, or more, maybe 1,000 times slower than registers. So it's better to keep data in registers, but the set of registers is not so big to have all the data in registers. For example, a stack. Stack is built when the program runs, and typically we cannot fit entire stack to registers, and it is organized in primary memory. There is intermediate memory called cache memory between registers and primary memory. It is to speed up access to data because it holds data that were accessed lastly or with similar addresses, because typically cache loads not only the cell to which we make the access, but it loads neighboring cells as well. Because the assumption is that we access the cells that were accessed previously or neighboring cells. Why not to arrange enormous set of registers? For example, 100,000 registers without cache, without primary memory, or with small use of primary memory. Because the speed of access is proportional to the cost. The memory organized as registers and cache could be very, very expensive, not acceptable for computer buyers. So we have a hierarchy between data flow: primary memory, cache, and registers. And we have mass memory, because all three, the registers, cache, and primary memory, are volatile. So we must have a place when we have stored data permanently. It is mass storage, typically on disks. Memory management is mechanisms that allow programs to access those memories efficiently just efficiently, because we will enter next properties later. But memory management deals only with primary memory, because loading to registers is prepared by a compiler. The compiler introduces to the program the instructions that load data from primary memory, calculate on them, and store the results in primary memory. And cache is arranged automatic. The programmer is not aware about existence and operation of cache. Several elements influence memory organization. For example, in modern computers, we don't have a single length of the computer word. When it was for 32-bit computers, or even not for them, previously 16-bit computers, they had 16-bit registers, 16-bit address, or not necessarily, because Intel had 20-bit address. And 16-bit bus, and everything was more or less uniform. Now we have internal registers that have the length of the word typical for given architecture. For Intel 64, it is 64 bytes, 4 bits for a single register. The memory word is equal to processor word, or sometimes double. Why? Because we often access 2 consecutive memory cells. So the memory prepares the, when we access 64 bits, memory prepares 128 bits to fast access in next cycle of the rest of the memory word. And bus length is even wider. It can be 256 bits. Why? Because through the bus, we load the content of the cache. And it is important to fill cache with data very quickly. So in modern architectures, it can vary. We can have different lengths of primary unit of data. And of course, it influences the addressing. Intel 16-bit is a good example of this. how the architecture of the computer influences the mode of addressing and the organization of memory. It was organized such a way that we have address register and segment register. And effective address is sum of those two. However, this register is shifted 4 bits to the left. So in fact, we add 2 words that are shifted to one another. And we have finally 20 bits address. 20 bits is mega. So first Intel PCs had a megabyte of memory. 20 bits. Of course, you see how the processor architecture influences the mode of addressing of memory and memory organization. A program cannot have less than 16 bytes because we shift segment register 4 positions to the left. Okay. What is the role of operating system in memory management? The effective address is the address prepared by the compiler. The compiler prepares instructions that manipulate on registers, memory, other registers, the part of instruction word, they mix them somehow and elaborate the final effective address. This effective address is prepared by the code, so it's prepared by the compiler. But it is not final because the programs coexist in computer memory. So when we talked about relocation, you know this datum register that is added to every memory access. So we have the mechanism of address translation. Address translation is converting effective address produced by the program to physical address in memory. Just the address of a memory cell. It is called address translation. Of course, it should be done under control of operating system. Operating system should prepare a program in memory such a way that it matches the way of address translation. One more property of address translation is protection. It is used not only to organize program memory and locate individual cells and to protect other programs from access of cells belonging to our program. When we talked about threads, the need for threads became from programmers' needs to run families of processes that work on the common target, common goal, and cooperate with each other. For the same purpose, the programmers needed operating system manufacturers to let them organize common memory parts between processes that have no common memory as a principle. threads occupy common memory, but processes do not. So programmers needed some fields of memory to access with protection of operating system that programs out of process family cannot access this, but processes in process family can. So such memory, common memory areas are organized by operating system. This is just to recall the rule in which dynamic relocation is executed. Between the registers of the program, there are two special registers not accessible to the programmer. Only operating system can modify those registers. They are datum and limit. Datum is added to every address generated by the processor. So we have virtual zero of the program somewhere in memory, of course, defined by datum. And if we use the address cell n, in fact, we use n plus datum that is somewhere in memory of the program. The second register, limit, is not used for relocation. It is used only for protection, because every address is compared with limit, and if it is greater than limit, it causes the exception in the program. So, it's called dynamic, just to recall, because we discussed this issue previously. It is dynamic because we can move the program in memory. For example, if we move the program in memory by 300 cells, we add 300 to datum and limit, and everything is still the same. And the program works in new location. Every program has its own pair of values loaded to datum and limit. So if we do the context switch between programs, we enter to datum and limit values allocated to given program, and the program works in memory area allocated to this program. And another program has its own pair of values. We will discuss the memory allocation model of Linux system, because it is very well organized. In Windows, we have a number of trade-offs and decisions made on needs of the programmers, and I don't like this model. So we will discuss only Linux model of program memory. The program has a code. Code are instructions in binary language prepared by the compiler. And typically in Linux, the program area is shared between the same program that is run several times. For example, in laboratory, when we have number of students sitting at terminals and accessing some server, a shell runs on every terminal. The code of shell is loaded to memory only once. Many students use many copies of shell. Every program call is executed through the additional copy of a shell. So we have an enormous number of shells when we have a number of students working in laboratory, but the code is only once. And data is separate area because every instance of the program has its own copy of data. This data area has some datum. It is virtual zero of this program. And additional area of system data. Those data are below datum, so a program cannot access those data. It can access, but every time a program must ask operating system to inform about what is in those data. The program cannot do it itself because it is below zero, virtual zero. And some shared data areas, maybe more than one. What is in system data? In every system, it is a file table, open file table. Every program has its own set of open files, and information of those files should be stored somewhere. So it is just in this system data area. Operating system remembers what is the file, what is the mode of opening this file, if it is for read or write or read-write, to allow only operations matching the opening mode. It remembers the current position in the file because every read starts at the position the previous read finished, and so on. It is in table of open files. And some informations about environment in which the program runs. It is current directory, environment variables, user and group ID, process ID, and so on and so on. I give examples here defining the meaning of those variables. But the nature of those variables is the same. They are pairs key value. I will show you how it works. Let us call CMD. We have a console. When we write set, it's in Windows, but it is just similar in Linux. We have quite large number of those pairs key value. Of course, no key can be duplicated because it's key. Home drive, for example, C. We can add new variables. Set new variables is value. It sorts by name. Oh, here. And what rule is typically used in operating system? When we run a program from a program, the child program gets all the variables of the parent program. Let us call CMD from CMD. We have new variable. But if we call externally, it has no new variable. So it is typical structure. And all those texts, pairs of text, key value, are held in such memory area, system data for a program. Because it is private to the program, it is not accessible easily. You see, I must call operating system to provide me the value of the variable. But it is not easily accessible to the program, but is owned by the program. The program is the owner, and all the children of the program get the set of environment variables of the parent. Okay. Here I must run exit 2 times because I am in nested console. Okay. And program data can be divided into some sub areas, but typically from the operating system point of view, it is uniform. Operating system does not distinguish here what is where, with some exception. Recall when we talked about how a new thread is run or how a program is run. The stack of the program must be initialized by the operating system or in cooperation with operating system. And parameters of the thread are filled by the operating system. So operating system must know where is the bottom of the stack of the program. So generally, this area is transparent to the operating system, but not entirely. Some data about this area are kept in operating system. It contains global data. They are global variables of the program. Heap, a part of memory in which dynamic data are allocated. When we execute, for example, in C++, we execute new object. This object is created in this area. It is the area in which a programmer has the control what variables or what new variables are allocated and what are disposed. In some languages that have garbage collection, we need not dispose, but we can. We can dispose an object, but we can leave this object until it loses all the references to this object, and the garbage collector disposes the object. This is heap. And a stack. Stack reflects the nesting of subroutine calls in the program. So the main is always on the bottom, and main calls other subroutines, and every called subroutine that has not finished has a frame on the stack. And because we have multi-threading programs, typically we can have many stacks. Every thread has its own stack. This is the information that operating system has about the data area of the program. Where are the stacks of the threads? Global variables. Typically in global data area, there are global variables and constants. When we write hello world, this writing hello world is put in global area. a stack. Oh, we have some structure of subroutines. Main is allocated by operating system partially. Because every frame contains two parts. In the literature, they are mixed in some literature, but in fact, there are two parts, because part of the frame is created by the calling subroutine and part by the called subroutine. The part prepared by calling subroutine is called activation record. For main, activation record is prepared by operating system. For every other, it is prepared by the calling subroutine. The rest, which has no name, it is the operation is called prologue. This part, even if we have an empty subroutine like that, this parenthesis says that a prologue must be put there by the compiler. So empty subroutine is not empty. The minimum that the subroutine contains is prologue and epilogue. So we have three subroutines. Main frame created by operating system. When we call A, frame of A is allocated on the stack. From A, we call B, which is allocated on the stack. When we exit from B, it is disposed from the stack, the frame of B. Here, the frame of, when we reach the end of A, the frame of A is deallocated from the stack. And finally, when the program finishes, the main frame disappears. This is the structure of stack frame. Here we see that as in Intel, the stack grows towards smaller addresses. Okay. So first, the calling subroutine deposits parameters on the stack. Parameters of the subroutine call. In some architectures, the result of the subroutine is pushed on the stack. Nowadays, it's seldom. Typically, nowadays, the result is passed in registers. But it can happen that the result is on the stack, the place for result. Static link, I will explain you how static link works later. And return address, because the last instruction of the calling subroutine is call instruction. Call instruction deposit the trace on the stack. And the program starts to run. It deposits the link to the frame of the calling subroutine, not to lose, because there is a special register called frame pointer that points to this frame, not in the beginning. It points to this point. Or frame pointer points to this address. And if we enter something to frame pointer, we dematch the old value. So the old value is stored here and restored in epilogue. It is stored in prologue, restored in epilogue. And finally, local variables are allocated on the stack by the prologue. Stack pointer always points to the top of the stack. frame pointer points to the middle of current stack frame. Namely, it points to the dynamic link. And here we have how the stack operates. Probably you know that from computer architecture course that we have stack pointer register. We have something that is pushed on the stack. So it is full descending stack. Full means that the top of the stack is full. Descending means that it grows towards lower addresses. And we put something on the stack. So full one now is one cell larger, empty is one cell smaller. Pop operation is reverse. We take something from the stack, it becomes empty, and we move the stack pointer to the higher address. Empty is one cell larger, full is one cell smaller. Okay, it's time to finish today. Next week we will discuss how those memory areas are treated during operations on processes in Linux.